today we'll be having two presentations. We'll start with the first one, which will be given by Professor Timothy Stark. He's a professor at UAC Department of Civil and Environmental Engineering with a special focus on geotechnical engineering. Over the past 25 years, his main research topic and teaching experience was about shallow and deep foundation. He will be also joined by Heather Shoup. She's AASHTO Central Office Geotechnical Engineer for this specific project that Professor Stark will be talking about today. She contributed a lot in the coordination and provided technical support for the 9 districts, especially overseeing the central soil and soil instrumentation laboratories. Professor, the virtual floor is all yours.
Great, thanks, Isaac. Good afternoon, everyone. It's a pleasure to give a presentation on our modified standard penetration test for drilled shaft design in weak rocks. Collaborators are Jim Long here at the University of Illinois, Ahmed Baghdadi, who is the grad student who's now in New York, and Reza Osuli at SIU Edwardsville, Heather Shoup, who's going to jump in the presentation in just a minute, and Mike Short in District 3 of IDOT. So here we go. We're talking about drilled shafts in shales. I'm getting an echo now. Is everybody else on mute? Drilled shafts in shales in Illinois, and so this is a weak rock and with an unconfined compressive strength between 10 and 100 KSF. Here's a couple pictures of drilled shaft construction in the shale. That gray material is ground up shale. It's a sedimentary rock that is prevalent throughout the state, and frequently IDOT structures such as bridges are founded on this material. So drilled shaft design in weak rock. We use the tip resistance here at the bottom and the skin resistance. We add those two together to get the total capacity of the drilled shaft, tip and skin. And here's the way we calculate skin resistance. And I want to highlight that we need this unconfined compressive strength of the rock to estimate the skin resistance by multiplying by 0.3. These are from load tests around the country in Illinois. And in the tip resistance, we also need an estimate of unconfined compressive strength and the shaft diameter and allowable deflection. So that led us to developing a procedure for IDOT to estimate the unconfined compressive strength of weak rocks throughout the state. So before the project, IDOT would frequently have a shale core drilling program that looks like this. The diamond bit core barrel is over here on the right where my pointer is. It's used to drill out samples of the shale, take those to a laboratory, and try to measure the unconfined compressive strength. Unfortunately, with shales and other sedimentary rocks, they can break during the drilling and sampling process. This is some typical shale core recovered throughout our project. And you can see it's difficult to develop an intact specimen to run a triaxial test to measure the unconfined compressive strength. And if you did, it may underestimate the unconfined compressive strength because of the disturbance caused during the drilling and sampling process. So that led us to develop a method for field measurement of the unconfined compressive strength. And that's where the standard penetration test comes in. The standard penetration test involves a 140-pound weight dropping 30 inches, and we measure the number of blows or drops of the hammer that it takes to push the sampler 18 inches or 45 centimeters into the soil or weak rock. Unfortunately, so the red line on this graph is where we have to get to run an accurate standard penetration test. With weak rocks and shales in Illinois, frequently we only go about 2 to 8 inches of penetration. So we're well short of the 18 inches. Even if we use 100 blows with a 140-pound hammer. So we had to come up with some meaning for running a standard penetration test that did not go 18 inches, frequently less than 5. So we came up with this process, which I'll illustrate via a video, where we measure the depth of penetration for every 10 blows. And then we use that data instead of a blow count that drives the sampler 12 inches, because we never get it to drive 12 inches. And we use these blow counts every 10. So notice the yellow mark on the drill stem. We're going to measure how much the rod penetrates and the sampler penetrates for every 10 blows. So there's the first 10, and now notice the rod's not moving much. So within 10 blows, we're on pretty good material. It only takes about 10 blows in this particular test to get down to undisturbed, weak rock. And this is Ahmed Baghdadi, who's recording the data right here. So this test could be wrapped up very quickly because the rate of penetration is very low now, and we don't need to go to 100 blows. So this is the data sheet that the IDOT prepared for the modified standard penetration test. There's the introductory material at the top, but here you see 0, 10, 20, up to 100 blows, and you measure how much penetration occurs in each of these 10. So if it stabilizes after 30 or 40 blows, you don't have to go to 100, which also shortens the amount of testing time and drilling time. So then we used the results we plotted on a graph of blow count versus penetration depth, like this. So here's one boring with 2, 4, 6, 8 tests. And we noticed that in the beginning, there's a fairly steep slope, and then it becomes pretty linear afterwards. And that allowed us to break up the penetration versus depth or blow count curve into 2 parts. The initial slope, which is a function of how much disturbance and cuttings are left in the bottom of the boring or core before the MSPT is run. And then the secondary or linear portion. And this secondary or linear portion reflects the undisturbed nature or behavior of the weak rock. And that's what we're going to use to calculate the rate of penetration, not a blow count. So here's the rate of penetration. We take the slope of the linear portion. So notice N dot or N rate is 1 over penetration depth divided by the blow count. So it's basically 1 over the slope. And that's what we're going to use now for drilled shaft design. And I'll illustrate that in just a minute. For people that have already conducted standard penetration tests and they want to try to estimate N rate, they can use their data for blows greater than 50, because notice the red line, certainly after 50 blows, you're past the disturbed part and you're in undisturbed shale. You can use those blow counts and estimate how much penetration was occurring over those last 50 blows and use that to calculate an N rate. And that way, drilling companies and engineers can use the database they have of prior standard penetration tests in weak rocks. So we prepared a test procedure for IDOT, and Heather Shoup's going to jump in and talk about the test procedure a little bit.
Hi, yeah, thanks, Tim. The test procedure is what Tim put together for us, so that when we have our drill crews and the consultants, they can go to the test procedure and they're all doing the same method, because it's a variation on the traditional standard penetration test. And right now, this is the version that you see on the screen. and we're in the process of incorporating it into our geotechnical manual so that it's more widely available and readily accessible. I'm going to turn it back over to you, Tim. Thank
Great.
you.
Thanks, Heather. Great, thank you. So to make this work then, we had to develop a correlation between N rate and unconfined compressive strength that we would use for drilled shaft design and tip resistance and skin resistance. So we went to 21 IDOT bridge sites that are founded on shale. Here's a few of them. And we drilled 2 borings, one in which we performed shale cores as traditional, and then right next to it, within 5 or so feet, we ran modified standard penetration tests. So we could correlate at the elevation of the shale core specimen to the modified standard penetration test. And we logged the core, as you see here, used a core barrel that gave us a 2-inch diameter core, which matched exactly the diameter of the triaxial specimen diameter that we needed. So all we had to do was cut a vertical piece out of the core, put it into the triaxial apparatus, as you'll see in just a minute. Here's the X's and green stars and red X's. That shows the distribution of the 21 sites across the state of Illinois. The orange and yellow and red areas are areas of shale. So you can see shale is a predominant bedrock material throughout Illinois. The 21 sites correspond to, say, an illite kaolinite clay mineralogy with liquid limit from about 20 to 50, so it would be in the low plasticity range. Here's a photograph of one such triaxial test to measure the unconfined compressive strength of a shale core where we had a modified standard penetration test. And here's the correlation between normalized penetration rate, or N rate, and unconfined compressive strength. So you can see the data, there's a lower bound and an upper bound, but the average trend line through the middle, you can calculate or estimate the unconfined compressive strength by 4.4 times N rate 90. And so this looks like a way to speed up the design process by just using field tests to design the drilled shaft. The upper and lower limit can be used to put a upper and lower bound on the shaft capacity. Now let me talk about the 90 part of N rate. So that corresponds to 90% of the theoretical energy of a standard penetration test. Because we measured the energy at each of these sites, this is in English units, same correlation, just in kips per square foot if you want unconfined compressive strength instead of kPa. And there are the 21 data points. So we, at each one of the sites we tested, we measured the hammer energy, how much energy was being delivered to the sampler. And you can see it ranged from about 77 to 100% with an average of 90. So these safety hammers that are being widely used, or automatic hammers, are very efficient. They deliver about 90% of the energy instead of the old cat and rope and cat head method where you were only getting about 60%. So we normalized the correlation to 90% of the energy. So if your site is delivering less than 90%, you can adjust it through this expression to get an N90. So you would use EM is the energy efficient. So if you were using 60%, you'd put in 0.6 here and divide by 0.9. The other correction factors are similar to a standard penetration test: borehole diameter correction, sampler correction, and the rod length correction. So the correlation's built on 90% energy using N rate. And this is some data from other IDOT sites where we went back and we predicted what the unconfined compressive strength would be from the MSPT test, and then drilled a boring and measured the unconfined compressive strength. So the solid dots are predicted, open are measured. So you can see a pretty good ability to estimate the unconfined compressive strength. And here's another site, laboratory versus predicted. The red symbols are the predicted. Okay, so last part is we checked the design procedure using the MSPT with 2 load tests. The load test used the Osterberg load cell that's placed at the bottom of the shaft, and then it lifts up the shaft and you measure the skin and tip resistance. This is one of those tests. And of course, we had to produce our prediction before the test, right? Got to put the prediction on the table first. So we predicted 70 kilonewtons would be the capacity and skin resistance of this test shaft. The actual measured side resistance turned out to be 76.23. So we were within a few percentage points of the prediction. So the MSPT looks like a reasonable way to estimate the unconfined compressive strength that then can be used to estimate the capacity of the drilled shaft. Okay, now, what about the MSPT-based design method? So now we could convert those equations, instead of being based on unconfined compressive strength, the skin resistance now is based on the N rate 90, or the rate of penetration at 90% energy. You multiply that by 1.3, and that gives you your skin friction. You multiply by the perimeter and length of the shaft where you want to calculate skin friction, and you have a direct calculation. And then you'll see that in the spreadsheet in just a minute. Here's the tip resistance, same. We use directly the penetration rate at 90% energy multiplied by 20, and then we multiply little q sub t by the area of the tip. So IDOT has created a nice spreadsheet that not only used for the data collection, but here is the design part of the spreadsheet. So now you go in at a particular elevation, you enter your MSPT data, it calculates the N rate for you in this column where my pointer is, and then you get the value of unconfined compressive strength and Young's modulus. And then on the other part of the spreadsheet, it shows you the plot from the MSPT and where the N rate, that's the slope of these red dashed lines. And then the next part of the spreadsheet gives you the shaft resistance, factored and unfactored, and it uses those design equations that I just gave you. So here's nominal side resistance, nominal tip resistance based on the relationships as a function of N rate 90. And there's the estimated settlement of the shaft under the surface loading. So all of this is contained in one spreadsheet. It can be used for data collection and design of the drilled shaft. So I think it's really a great tool for bridge designers and other deep foundation design applications involving drilled shafts. Okay, so quick summary. The outcome of the project, I think, is improved drilled shaft design and weak rocks for the Illinois Department of Transportation. This is leading to some cost savings for IDOT in the use of less conservative values of unconfined compressive strength, which means smaller diameters and smaller lengths of the drilled shafts are required, which gives a less conservative design. In addition, there's less shale coring and less laboratory testing time required, and because of that, it reduces cost and time. That gives us a shorter design cycle for deep foundation type structures that IDOT is dealing with. Finally, the implementation is facilitated by IDOT developing this spreadsheet for not only data collection, but design of the drilled shafts, which I think is a really great operational spreadsheet. So I'd like to wrap up acknowledging all the people that were involved in the project. Bill Kramer was chair of the TRP, Technical Review Panel. He was head of the bridge group there in Springfield. Brad Hessing, Heather's on the line, Mike Short in District 3, Brian Lanningham, District 6, Dan Tobias, Greg Heckel, others. Nasser was a big help through the FHWA. Chad Hodell coded the spreadsheet, and Tom Casey, Terry McCleary were industry people that helped with the implementation of the modified standard penetration test. So, Heather, if you want to jump in before questions, or if you want to go to questions.
I'm fine with going straight to questions because I basically covered what I needed to on the MSPT slide. Thank you.
Okay.
So now we can open the floor for questions. So if you have any question, please go to the participants tab and then click on raise your hand so I can see who has a question and I can moderate the question. Mingu, go ahead.
Thanks, Isaac. I have a quick question. My question is, can we get the linear portion all the time? Because Professor, you mentioned that often hammer blow cannot reach 100 because of the kind of less weathered locks, harder portion. So I guess sometimes it might be hard to get the linear portion to get the end rate.
Okay, so I'm backing up to the diagram for the linear portion and the initial portion. We actually get to the linear portion fairly quickly, and we usually can get there within 10 or 20 blows, certainly never more than 50 blows. So we rarely have to go to 100 now. And in fact, in the video, if you watch the, let me see if I can go back. You watch, it'll only take 10 blows, and watch the yellow mark right there on the drill rod. It'll only move for the first 10. Let's see, let me speed it up a little bit. Okay, that's 10 right there. Look, the mark is barely moving. It's on that number on the stick rule. Maybe a quarter of an inch. And that's after just 10 blows. So did that answer your question?
Yes, thank you very much, Professor.
Great, good, good.
Any other question, guys? I think that's it for the question. Thank you so much, Professor, for this very nice presentation. And thank you, Heather, too, for joining us today.
Great. Thank you.
Thank you so much.
Yeah, you're welcome.
So now we have our second presentation. It will be given by Qamhia. He is a postdoc at UIUC. He received his PhD degree from UIUC in transportation geotechnics. And also he received his master from Wisconsin, Milwaukee. Today he'll be giving a presentation about the durability aspect of chemically stabilized quarry byproduct that is used usually in the base and the subbase.
Thank you, Isaac, for the introduction. Good afternoon, everyone. Can you hear me well?
Yes, we can.
All right, perfect. So good afternoon and welcome to another Kent seminar. As Isaac just mentioned, today I will be presenting about durability aspects of chemically stabilized quarry byproduct applications in pavement base and subbase. This presentation will be actually based on a TRR publication, which was recently accepted for publication in the Transportation Research Record. And I would first like to start with acknowledging my team or the collaborators on this project, as well as the co-authors on the paper. Professor Errol Tutumler, who was the PI of the project, Professor Hassan Ozer, formerly with UIUC and now with Arizona State University, the co-PI, myself and Hussein Bowler, or Dr. Hussein Bowler, PhD student at UIUC formerly and now with Open Road Paving Company. And from IDOT, we have Heather Shoup, who was the TRP chair of this project, as well as Andrew Stolba, who was also a member of the TRP chair in this project. So basically what I will cover in this presentation is going to be based on a recent report of ICT or a publication called the ICT R27-SP38. That's a special project to study the durability aspects of Quarry byproducts, which is based on a previous bigger study that we did for the accelerated pavement testing of many sections of Quarry byproducts investigated in the field, which is the ICT R27-168. The objective of both projects, the bigger project and the follow-up project, which is basically this presentation, was to evaluate sustainable pavement applications for Quarry byproducts in subsurface pavement layers. And you can here see the link for the publications if any of you is interested. So basically, what are the evaluated Quarry byproduct applications that I will cover? And for those of you who don't know what Quarry byproducts are, those are sand-sized particles that are produced as part of the processes that happen in quarries, such as blasting and screening, that produce these byproducts. In this presentation, we're going to focus on some bound applications of Quarry byproducts in base and subbase materials. So these what are the applications that were studied as part of the bigger project for accelerated pavement testing. We had Quarry byproducts as a base material stabilized with either cement or fly ash. Some of the sections had some Quarry byproducts mixed with recycled materials with them, either wrap or RCA, recycled concrete. And we had some sections also that were sub-base sections, so sort of an inverted pavement applications for Quarry byproducts stabilized either with cement, 3% cement or 10% fly ash. Just quickly showing some of the test sections or the test sections that this study will be based on and what are the chemical compositions. As you will quickly see, there were two types of Quarry byproducts in the sections, QB2 and QB3 here. Some of the sections had cement as the stabilizer, some of them had fly ash as a stabilizer, and some of them had recycled materials, either wrap or recycled concrete aggregates. Just showing a quick plot of some of the results of the bigger accelerated pavement testing study. This is showing the field performance or the surface rut measurements in those test sections. And we had a threshold of 1/2 inch or 12.5 millimeter of rutting here to stop the experiment. Most of the test sections, we went up to 140,000 passes, and we did not exceed that threshold for most of the sections. You see at the bottom here, the better performance sections or the best performance were the ones that had recycled aggregates with Quarry byproduct and cement, and the ones that had the highest rutting were the fly ash stabilized test sections. So what inspired this project, or how did we get into investigating the durability aspects of this section? Actually, this is part of the reason. This shows the test sections after they were trafficked and trenched to get some depth or height measurements. What we saw after having those test sections open, with trenches open for more than a year, and having those test sections built for more than 3.5 years when these pictures were taken, is that the subgrade underneath many of the sections, as you see in those pictures, have eroded. But then those Quarry byproduct sections or subsurface layers were just standing there as cantilever beam on top of the eroded subgrade. So AASHTO reached to us with the idea of why don't we complete that project that was done with the field performance and do some durability testing, just get advantage of those test sections, get some field samples and test them for their durability in the lab and see how durable those samples are and what are the numbers that we get for soil cement loss, which is what defines durability in those tests. So basically that was what was done, and just to fill you in with the details, basically we tried to core these test sections first and to try to get just cylindrical cores from the Quarry byproduct sections, but that was not very successful, because if we do a wet coring method, what happens is that the materials will disintegrate and we will not be able to get an intact core. If we try a dry coring method, on the other hand, so that we don't use any water, because these materials are not very fine like concrete, but they are actually a little bit rough on the surface. They actually create very high friction and they get confined into the drill bits, and it's very hard to also get an intact sample out of the drill bit for testing. So the third method that we tried, and I would like to acknowledge here or thank Greg Renshaw, who I see him watching us, who helped with this field extraction of the samples was to bring a mini excavator and then try to get big chunks, unexposed chunks of the materials, dry them in the lab, and then so cut them into samples. So the idea was it's not going to be easy to cut them into cylindrical samples, so we went into an inscribed prism or a cuboid, which have the size of a circle, or a prism inscribed into a standard Proctor mold, which has a 4-inch diameter. And we cut the samples into this cuboid size for testing. Also, we wanted to do some lab samples for comparison and to compare and contrast with the same mixes. So for those, we used the Proctor sample size for the preparation. These are some images here that show the preparation of the samples. So we use the big saw cutting equipment for cutting the field samples into the cuboids or the prisms. And this is actually a saw cut that is intentioned or used for big rock cutting. And as you can see here, this is the final samples that were cut from those big chunks. So what you see here is 6 or 7 material combinations, 6 material combinations actually, of the materials that were cut. In total, we had 4 samples cut for each material combination, 2 to test for wet-dry durability and the other 2 to test for freeze-thaw durability. As you can see, the quality of the sample in terms of how good the surfaces are will depend on the materials. So if you look at the center one here, these are the ones that have either FRCA or just a QB. They have smoother surface. The ones that have the wrap, they have more irregular surfaces than the other samples. So that was for the field samples, and also for the lab samples, we prepared the samples in the Proctor mold. We had to get some help from the machine shop to actually make this a split mold so that we can keep the samples intact upon preparation. And we prepared those samples and cured them. One thing we were interested into is that for the concrete samples, or the RCA, recycled concrete aggregates, we had some bigger particles in the field test sections. So we wanted to strip those samples into aggregates that are just less than 3/4 of an inch in size, just to be able to compact them in a Proctor mold size and not affect the results due to large particle size issues. This is here showing the curing of the lab samples. So these were moisture cured in a moisture room at 100% relative humidity and room temperature for 7 days. And just a brief introduction about what are the lab testing that were done for this study. So we did the lab testing for freeze-thaw durability and wet-dry durability. And basically freeze-thaw means that in each cycle, the sample is frozen and then thawed and then tested. For wet-dry, it is a wetting and drying continuous cycle. So for each cycle, it's a wetting and drying cycle. And we also wanted to do some unconfined compressive strength testing. And the idea with the unconfined compressive strength testing is that the samples that were constructed in the field were constructed 4 years ago, almost before this study was done. And then for the new samples prepared in the lab, we had to bring new cement and new fly ash because of the shelf life of these materials. So we wanted to see how close those are to the ones that were actually constructed in the field in terms of compressive strength. For the durability testing, what we used was the standard AASHTO Central Bureau of Materials standard test procedures for freeze-thaw and wet-dry for soil cement mixtures. Those are actually based on the AASHTO procedures, AASHTO T135 for wet-dry durability and AASHTO T136 for freeze-thaw durability procedures. And we conducted these testing on all the materials that were collected from the field and the lab. We had in total 7 mixes, 2 replicates per each mix for each test, either freeze-thaw or wet-dry, and then 2 sources, which are the field and the lab. So in total, there were 56 samples, 28 were freeze-thaw samples, half of them were field, half of them were lab, and the other 28 were wet-dry samples. Showing you some pictures here of the test procedure. This testing for durability was done in IDOT in Springfield in the Central Bureau of the Material with the help of Kurt Schmuck from the Central Bureau of Material and his colleagues over there. This is showing you, and I'm splitting the samples now in terms of naming into round 1 and round 2. So round 1 is the round 1 of testing, which was done for the lab samples, and then round 2 is the one that was done for the field samples. Just showing here the procedure or some images of the procedure for the wet-dry durability testing. So it starts with the wetting and the soaking, and then the brushing of the sample, and there's a standard brushing procedure, so that actually when we had to go to a different shape in the prisms in the lab, we were fully good, or in terms of following the standard, the AASHTO standards, because of the number of strokes that we have to give every area in the sample. So that's something that has to be done and checked. And then at the bottom here, you will see the samples tested for wet-dry durability at different number of cycles. So that's after 1 cycle, that's after 7 cycles, and that's after 12 cycles. And the test is terminated at 12 cycles of testing as per the AASHTO standards. Here, we're quickly showing the results from the wet-dry durability samples for the different mixes. Usually, the results for the durability of the soil cement is presented as an average soil cement loss in percentage, or how much of the dry sample is lost at each cycle. So the results that are shown here are the average soil cement loss after 12 cycles, or after the termination of the test. And what you see here is that for the wet-dry durability for the lab samples, all of them had wet soil cement loss after the termination of the test of 10% or less on average, which is considered good, given that this is usually the standard of IDOT, is that 10% or less is acceptable as material for use, or a durable material for use following this test. The second part of the round 1 of testing was the testing of the freeze-thaw samples. That was a little bit of a different procedure, because you have to put the samples in a freezer and then thaw them in a moisture room and then test them. And here I'm showing some samples after cycle 1 of testing, after cycle 7, and after cycle 12. One thing to mention here is that freeze-thaw testing is a much harsher test than wet-dry testing. So you would expect the numbers to be higher usually from the freeze-thaw testing in of the same mixtures of materials than when you do the wet-dry durability testing. And that's actually what the results here are showing. So this is the same thing. That's the average soil cement loss after 12 cycles of testing for the different material combinations. You would see here that some of the material combinations went way high, like exceeding 60% or 70–80% in some cases, while some of them were in the ranges of 10 to 20% of soil cement loss. I'll talk later. I'll discuss more details about which samples were better performing, which samples were less performing as we move on to the field samples, just for the sake of time. One thing I would like to mention here is that since the results are based on 12 cycles, if some samples did not actually finish the 12 cycles, or they failed disintegrated before 12 cycles of testing, what we had to do is we had to extrapolate the graphs that we get into the 12 cycles, so that we can estimate what is the estimated soil cement lost after 12 cycles of samples. This did happen for a few samples for the lab prepared samples, and then for three actually of the mixes in the field samples, as we will show later in this presentation. All right, round 2 of testing, which is the more interesting results, was actually for the tests or the samples that were extracted from the field. These are the different combinations of materials that were tested for the freeze-thaw durability. It's the exact same procedure that I showed before, but we can see first some samples of the wet-dry durability at the beginning of the test, and then after the end of the test. And these are the results after 12 cycles of testing. So what was interesting here in the lab samples, or in the field samples, and how they were different from the lab sample, is that if you look at the different material combinations, fly ash samples had 18 to 20% almost of soil cement loss after 12 cycles, which was different from what we saw for the lab samples, where all the samples for wet-dry durability had the less than 10% threshold loss of materials. So one thing that this told us that fly ash samples were not as durable after they've been in the field and exposed to many cycles of freeze and thaw before those samples were tested, because as I mentioned earlier, those samples were in the field for 3 to 4 years before they were extracted and tested, and they were exposed to loads and environmental conditions and numerous number of freeze thaw and wet dry cycles just before they were tested in the lab. The other interesting thing that we realized is that we had two sources of QB, the QB2 and the QB3, and then I know the number for QB3 is still low. We're talking about 4 to 5% of soil cement loss. But if we compare that to all the other samples that had the QB2, they were more or significantly lower soil cement loss after the 12 cycles were finished in the testing. To show the results here, this is more comprehensive results for the different mixes. I have the combinations of the materials shown in the table at the bottom. But what this shows here is cycle by cycle, how did the wet-dry soil cement loss happen until the end of the 12 cycles. What you see here is that all those samples here at the bottom are the ones that have the QB2 or QB2 mixed with some recycled aggregates, either RAP or RCA, and stabilized with cement. This is QB3, so it's a little bit higher. And the ones here on top that exceed the 10% going up to 18% on average, or 16 to 18% on average, are the ones that have fly ash in them. So QB2 with fly ash. So that was one of the big conclusions that we had, is that the cement sections in the field were more durable than fly ash. That was the obvious conclusion from here. Now this is showing, again, the test for freeze-thaw durability for the lab samples. And I'm showing here on the right side of the presentation some of the best performing samples. Sale 2, section 1, that's QB with RAP. It's not necessarily the best performing, but one of the good performing samples. And then some samples that disintegrated before 12 cycles were completed. And that's where you have to actually extrapolate the curve into the 12 cycles average estimated soil cement loss. And as I mentioned earlier, this freeze-thaw test is usually much more harsh than the wet-dry test. What was interesting again here in the lab samples is that if we look at the fly ash samples, then that's expected that we go to 70, 80% now, or 100% or total disintegration at the 12 cycles. And the reason is because if they had 18 to 20% in wet-dry, then those numbers would be much, much higher in freeze-thaw. What was interesting again is that if you look at the QB2 samples now, then even though these samples were exposed to many freeze-thaw cycles in the field early on, and also they were tested with this harsh test, you would see that many of them had very low losses or soil cement losses after the 12 cycles. So look, for example, at the Quarry byproduct 2 with cement here, or Quarry byproduct with RCA of cement. Some of them didn't even exceed the 10% threshold that is usually used for that, even though they were exposed to field composition, field conditions and environmental conditions in the field for a while before testing. So one thing to notice too is that QB3 now, the one that had Quarry byproduct 3, another source of Quarry byproduct, also didn't perform very well in the freeze-thaw testing from the field samples, and they had a very high soil cement loss, or the full disintegration of the sample at the end of the test. So to show the results more comprehensively, again, at the different number of cycles and how did the soil cement loss continue or happen with time, you can see here at the bottom are the different combinations, mostly the ones that have QB2 with cement, while here on the top you have the ones that have QB3 or QB2 and fly ash. So this is again another conclusion here, that QB2 was more durable than QB3, and also the same conclusion again, which is that fly ash was much, much less durable than samples that had cement. This is just a comparison here for the field samples with the lab samples for wet-dry durability and then freeze-thaw durability. What's interesting here is that if we eliminate fly ash, what you see is that the field samples had better performance than the lab samples, and this will lead us to one of the conclusions and recommendations that we did to IDOT following these results. The same thing here you can see for the freeze-thaw durability. The field samples, which are shown in green striped lines, are more durable or the same durability at least than the lab samples, except for the ones that have either QB3 or fly ash combinations, which were less durable. Before I jump into the conclusions and explanation of these results and what is happening, one thing to mention also is that we did the unconfined compressive strength testing for those samples. And the idea was to compare the strength of the lab samples that were newly made for this study with the ones that were made 4 years ago before we even constructed the test sections, just for the sake of comparison of the strength and to see if they were the same or not. The results show that relatively the current results for this special project and also the older project, the unconfined compressive strength was not statistically significant for most of the material combinations, except we found in one of the test sections that has QB2 with fly ash, and that one actually the new results were from the ones that were tested newly were statistically significant and higher than the ones that were tested in the previous study. One more thing here is showing some cube test results from the field samples. So these lines here show the minimum, maximum, and then the dot is the average results from just extracting cubes from the field samples and testing them for freeze-thaw durability. And what you see here, for example, what I have highlighted here in red, comparison between one test section that had QB2 with cement and the other that has QB3 with cement. So you would see here that QB2 was much higher strength in the field than QB3. So in general, the durability results that we got were actually more in proper match with the test results of the cube unconfined compressive strength from the field samples than when compared to the lab samples. And the same thing for the lab samples. They were in good correlation when compared to the lab samples. So one thing to highlight here is the density of the materials that were extracted from the field. And one thing to mention here is that we don't have much control about trying to get the relative density of 100% or not, because if you remember, we were extracting those big chunks of samples and they were very hard to, first of all, find and extract intact samples that are not broken during the cutting process. So that was actually a big factor in determining what final relative density we get for the sample. One thing that you would notice here that the fly ash samples had low relative density compared to other samples, as well as the sample that had QB3 was also of a lower density compared to other samples. But is that density the only factor that we have and that is contributing to the low wet dry and freeze-thaw durability of the QB3 and the fly ash? Well, if you compare other samples that performed well and they were also at a low relative density, then that's obviously not the only reason. And there's another reason, which we were looking at the X-ray deflection or X-ray fluorescence results for QB2 and QB3. And what we found is that their chemical composition is significantly different. So if you look at QB2, for example, this was a dolomite source, and dolomites usually have higher magnesium oxide contents than calcium oxide content compared to QB3, which is very, very low on magnesium and much, much higher on calcium oxide or limestone content. So it's actually well known and established in literature that usually the calcium goes into reaction more quickly than the magnesium, while the carbonation of the dolomite limestone contributes to more long-term strength gain of the materials. So we think, and we would like to proceed actually and pursue testing and checking this theory, is that what was happening with our samples is that when we had QB2 with more dolomite sources, that's actually going to be more durable and give you higher durability for materials constructed with QB. So dolomite sources would actually contribute to better field performance as well as better durability on the long run of materials. I know I'm running out of time, so that's going to be actually my last slide here about the concluding remarks. I have some conclusions here summarized from the bigger project or the accelerated pavement testing project about the performance of the samples. So what we saw is that the samples that were blended with RAP or RCA with QB and cement had better performance than other samples, and usually the ones stabilized with cement consistently showed better performance than those with fly ash. So what about how this compares to the durability testing? We don't have a one-on-one ranking, so the best performing section in field performance is not necessarily the best performing in durability, but overall the trends are the same. So the ones that have cement are more durable than the ones that have fly ash. So that conclusion is the same. And also we saw that for the durability samples, all of the lab samples actually had satisfactory wet-dry durability and also the wet-dry durability was much better than the freeze-thaw durability for the majority of the samples tested. Another thing or another conclusion is that the chemical composition of the Quarry byproduct was found to have a significant effect on the durability, particularly when we're talking about the long-term durability into consideration. And that's what we saw with the dolomite. QB2 had outperformed the limestone QB3 in the observed durability trends from the field. One thing to acknowledge here is that the density would still have an effect, but we think that the chemical composition would have the biggest effect on the durability trends that were collected or observed from the field samples. Last, I would like to acknowledge some of the people that helped or contributed to this project. Of course, we'd first acknowledge the ICT R27 SP38 technical review panel for their input and recommendations during the scope of this project. Mr. Kurt Schmuck from IDOT Center Bureau of Material, who helped with the testing of the materials. Mr. Greg Renshaw from ICT, who helped with the extraction of the field sample. Also Mark Killian, the machine shop, and Tim Prunker from the machine shop at University of Illinois. And then from IDOT, Kyle Henselman and Muhammad Al-Otawi. Thank you very much for listening. And if you guys have any questions, I'll be more than happy to respond.
Thank you, Isam, for this very nice presentation.
Thanks,
so guys, again, if you have any question, please go to participants and raise your hand so we can see who has a question and moderate the discussion. Isam, I actually have a quick question, but sure. It's not related directly to what you're doing. It's more like general. So whenever you were showing that you were preparing the specimen in order to check the theory that you had, or like the conditions of having the base or in the subgrade, sorry, in the base or in the subbase. How do you make sure like the size does not have an effect of the sample? Did you try, not you, maybe in general, did you guys try like a bigger specimen or a smaller specimen to see how much the size of the specimen affect the results?
Right. So that's the idea behind, if you remember, I mentioned in one of the slides that we were limiting the gradation or the grain size distribution of the samples that were tested with the recycled concrete aggregates to 3/4 of an inch or less. And that's actually boundary effect criteria that is usually checked with AASHTO and ASTM procedures, is that you have a limited sample size. Let's say this is a 4-inch size mold or a 3-inch mold size mold. Then you have to limit those large particles that will actually affect your results more, because if you end up having, for example, a 1-inch or 1.5-inch particle that is in a 3-inch diameter sample, then that's half of your sample, and that has a big influence on your results. So part of the standards is actually to limit your gradations of the materials that you use to prepare your field samples into what is acceptable within the size of the sample that you prepare. That's one aspect. The second aspect is actually about the size of the samples. So the size of the samples, especially the lab samples in particular in this study, were actually standard samples as recommended by the AASHTO procedures and the procedure by the IDOT CBM. And for the field samples, since they were not standard sizes or shapes, at least, we had to check that we actually conform in our testing to what is recommended by the ASTM standard in terms of how many strokes each area gets and how many strokes each face of the cuboid that we were having had to have, so that we have comparable and reasonable or actually good results that conform with the standards. Does that answer your question, Isaac?
Yes, thank you so much. So we have just one more question from Omar. Omar, yes.
Yep. Isam, thank you for the presentation. I was wondering if you can speak a bit to the value of accelerated pavement testing and you know, how compared to just, you know, running a few experiments in the laboratory, accelerated pavement testing can provide you with insight, which can be, you know, I don't know, you know, it's what you think is probably useful, such as, for instance, you know, applications immediately on sites, etc.
Right. Actually, yeah, I will answer your question, but this reminds me of a point that I probably forgot to mention during the presentation, is that, for example, when we tested the lab samples versus the field samples, what was different is the amount of curing that you had in the samples. So in such a particular test setup, if you test just lab samples that are cured for 7 days, and then you want to get the performance for long-term, 20 years in the field, then you might be basing your testing on misleading results, because you're omitting all the curing that will happen in the field and the long-term effect of the curing. So, for example, in such a setup that we did, what we have as a recommendation, if you want to do lab testing, something that is quick and less expensive, is that you probably do an accelerated curing of the material, so that you cure them, instead of just 7 days at regular temperature, you cure them to higher temperatures or longer curing time, so that you are actually seeing more of what you will see in the field. So that's one thing that I forgot to mention. The other thing is your question about the accelerated pavement testing and how it contributes. So basically, it just gives you a step ahead, or more further information than just lab samples. So lab samples or lab scale, you're more limited to the size of your experiment. As Isaac also had his question, you're more limited to the effect that you see, like the short-term effect. So when you go to accelerated pavement testing, that's a step further, because now you're building full-scale test sections. So you're eliminating the size effect. You're also exposing those test sections to more realistic loading. So instead of hammer load in the lab, for example, or an actuator loading, you're now using tires, actual full-size truck tires, and testing passes, so number of passes. So you have the dynamic aspect, and then you have the realistic aspect of what is happening in the field. So it's more of a step further between what you do in the lab, which is very basic and very cheap, and what you will see in the field after 20 years or certain years of experience. So it's an intermediate, reasonably priced thing to do accelerated pavement testing. Does that answer your question?
Tumler, I think he has a comment or maybe a question that he wants to add.
Mm-hmm.
Professor Tumler, yes.
Yes. Hi. I would like to just thank Isam for a great presentation, and I would like to add one point to actually what he has made very nicely, which is, you know, what we found over the years with testing dolomite in many different studies, including this was the third accelerated loading APT testing study, actually, that we were able to finally study durability aspects of maybe at least three winters of cementation and what we call this dissolution precipitate kind of chemical reaction effect on the dolomites durability results. Very interestingly, we see a lot of the cementation taking place with our dolomites, and I think there is more to understand about how dolomite with you know, up to 12% fines in regular even aggregate gradations can be used with little cement to build the low, medium volume roads, our county roads. That may be a very good alternative. I think there is something that definitely we need to understand better about the good performance of the QB2. And I think this means a lot of savings and significant maybe savings from the point of building local roads, some county roads, if we can actually make them survive several years. I mean, that's, again, a huge overall impact for road construction in Illinois. And probably to learn more about that for the rest of the states and all over the world. So I think there's a lot of very interesting, significant, impactful results here we need to pursue further. That's how I feel. Again, thanks, Isam, for the good job.
Thank you.
Thank you, Isam, for this presentation. The time for the presentation is over, but I think Javier has a question. So whoever has something, has another meeting now, that you can leave the presentations over. And if you want to listen to Javier's question and his discussion with Isam, you can stay online. Javier?
Yes, Javier.
Hello.
Yes.
So I have a quick question and then another one. So the quick one is, what is FRCA?
FRCA is fractionated concrete recycled aggregates. So fractionated means that we only use the coarse portion of it, and then RCA is the recycled concrete aggregates.
Okay, and then could you elaborate on if with your results, if not, then just by your experience, I was curious on if these Quarry byproducts are giving enhanced durability to subbases and bases. I mean, compared to a base without Quarry byproducts, how does it look in terms of durability?
Yeah, so the idea is that these are cemented materials. So they have either cement or fly ash combined with the Quarry byproducts. And what you usually do is you don't check if they enhance the durability or not. It's more of a mixed design that you need to pass two aspects. The first aspect is that you need to pass a minimum unconfined compressive strength. And the second aspect is that you need to pass minimum requirements for the soil cement loss by wet-dry durability and freeze-thaw durability. So that's how they are designed. And what you do is that you refine your designs by increasing your percentage of cement or the cementing agent, or you refine your gradations so that you can pass both criteria. So what we did in this test in particular is that we mostly had Quarry byproducts, or those sand-sized materials tested in the in this project. So basically either that or mixed with some recycled materials. So if you want to ask how they will contribute to the durability of other samples, like if they're mixed with other materials, they might actually, based on the idea is that if those fine materials can actually react and over time contribute to the cementation of those layers, they will actually contribute to that. But that's something that I cannot just answer on top of my head now. I think it needs probably some testing and verification and validation before we know for sure if they will contribute enhancement in the durability, or keep it at the same, or actually worsen it a little bit.
Thank you, Isam, for this nice presentation. Thank you for answering the question that we had. And that's it.
You're welcome, guys. Thank you very much for having me. All right.